Thank you. So also maybe if I don't see such an important message, please unmute and ask, right? Okay, good. So we just looked at these two extensions. One is where the schedules arrive one by one. We don't know when they are going to arrive. And the other one where the schedules also have a starting point or a release time, and they cannot be scheduled before the release time. So this actually, so you can try designing a greedy algorithm, but greedy does not work in this case. This makes the problem harder, and maybe we'll revisit this particular problem later in the course, okay, when we have the release time also. So you can think about it, why, where we were using that, everything could start with a start point and does not have a fixed start point in the proof or in the previous problem, and why the algorithm would fail if the problems have a start point and so on. Okay, so this is for you to think about. Now, today the problem we are going to look at is optimal caching. Okay. So, have you guys done operating systems course?
No, sir.
Okay. So good. So you must be remembering. Okay, there was this concept of caching. That okay, we have this main memory. Which, like, have this, and in between sat this thing which was the cache. And this was like, this was the fastest, this was like, fast, but like this is slow as compared to that, and this is something in between. Registers have like, very small memory. Main memory is significantly larger. And again, cache is something, relatively smaller than again in between. And what is so this is the trade-off that, okay, you make it smaller, but you make it slightly faster and so on. So the idea is that we keep some of the things in the cache that we are going to use like, frequently, and so that we don't have to access the main memory on every memory reference. So you must remember this, like, concept. So I'm not going to delve into why caching is important or what caching does, but we are going to look at, like, one theoretical formulation of it and how we solve this problem, or how we actually get it into caching. Okay, so let the main memory have n chunks, like 1, 2, and for which references can be generated. Okay, so this is n pieces of data. Okay. And suppose the cache can hold k pieces of data. Okay. And now, so this is like, so cache is much smaller. So the original main memory has n pieces of data, cache has k pieces of data. And now suppose some m many references, m memory references are generated, and call them, let's say, d1 to dm. Okay. And now we want to keep some k items in cache. Okay. So if the request, if the reference or memory request is in cache already when the memory reference is generated, that's good. That's what we want, because that will reduce the cost of, accessing the main memory. And if not, then we need to bring the chunk from main memory. And if there is no space for it, if the cache is already full, then we need to evict something. Okay, so this is something for which we want to now have, an algorithm which will decide, okay, so what to bring in, what to evict, and so on. So this is what we want to minimize, and this is called cache miss actually. When the memory that is referenced is not there in the cache, and that is called a cache miss, and that will require doing something with the main memory, which will take more time. So this is what we want to minimize. Okay, so want to minimize. Okay, good. So now a cache maintenance algorithm that determines the eviction schedule. Right? Which item should be evicted and which item should be kept. Okay, good. So let's just see how or what can be done. Okay, so let's just try to go towards designing the algorithm. So, and this of course will determine the how many cache misses of are going to happen. So let's just look at one example. So suppose there is some three pieces in the main memory A, B, and C, and suppose this is the what you get is the sequences. Let's say A, B, C, B, C, A, B, and let's say that K is equal to 2. That the cache can hold 2 of these, right? And so initial 2 is always going to be so there are some compulsory misses, right? When the cache does not hold any data, then it has to bring in the data whenever it's referenced, right? So initial K misses are going to be compulsory misses. Okay. So we are not going to count them because no matter what the algorithm does, first it has to miss the first K references and it has to bring in the data. So we'll not be worrying about that much. Okay. So let's assume that initially the cache has already A and B. Okay, that those misses have happened, and then because only after that these things start to matter. Okay, good. So now let's say that the algorithm evicts. So now the third reference is C, right? So now when C comes, then the algorithm needs to evict either A or B, right? So suppose it evicts A here. So the schedule will put that A is evicted here. So after that, the cache becomes, so C is brought in and A is evicted. So it becomes C and B, right? Now B comes, so B is already there. So we don't need to evict anything. B is already there. So it remains so we don't change the cache, it remains the same. Okay, let me just write it down for sake of clarity. CB, it remains there. Then again C comes. Again, we don't need to evict anything. Okay, I can go faster than this because you guys have already seen such things. And then A comes. Now again, we need to evict something. So suppose the algorithm decides to evict C. Okay, so now we get A and B, and then we get whatever. B is already there, so we get A. Right? So this took 2 misses, right? After the cache already has. So we'll be counting only the misses which are not compulsory. I mean, which the initial forced misses will not be counted compulsory or forced misses. I mean, you can give it any name, but you get the concept, right? Okay. So this one has 2 misses. So the question can be that can we reduce this? Can we get it less than 2 or something like that? Okay. So that is what we will try to address. That what is the optimum way to do this, right? So is this clear? At least the setting is clear that what we are trying to do. We have n pieces of data. We have k sized cache, which is smaller than n, and then we are trying to basically keep some k so that the memory references generated will generate the minimum number of cache misses. Okay. Any questions about this? No questions about this setting. Okay. So now let's look at the the algorithm which was given by which is called like Reddy's algorithm, which was given in like 1960 actually, long ago, and what does he say? That suppose di needs to be brought into cache. Okay, then evict, and it's all not already there. Then evict the item that will be needed farthest in the future. Okay, so let's just look at an example. What does it mean? So, I mean, you might have seen it again, but let's just quickly go through an example and see. So let's say again now you have 4 pieces of data and the cache is 3. Let's say so you have A, B, C, D, or 5 pieces of data. It's D, B, C, and so this is the memory references and the algorithm needs to. So let's see what this algorithm will do. So initially, let's again suppose that the cache is A, B, and C. Now D comes. So D comes here, and now among A, B, and C, which one is farthest used? Can someone tell?
So C.
C is the farthest. So let's evict C here. So let's write C there. That C is getting evicted, and then the cache becomes A, B, and D. Right now, A comes, no miss. D comes, no miss. E comes. So that is a miss. So E is not there. So we need to evict something here. What should be evicted among A, B, and D?
B.
B, right? Because B is the farthest here. So you evict B, so you get A, E, and D, right? So you evicted B here, right? And now A comes, you are good. D comes, you are good. Now again B comes, and now you can evict anything except like C is also not there, so farthest in the future does not really matter. So you can evict anything. So you get here, let's say B, E, and D because you evicted A, and here you evicted again anything. Let's say B itself. So C, E, and D. So this is what a scheduling algorithm will do. It will, for each reference, will figure out what to evict, right? Either the it is already there or it will evict something, right? So is the algorithm clear? What the algorithm does? I mean, you must have seen it in the operating system course also, but there you might not have done the proof that this is actually an optimal algorithm. Okay.
Sir, we need to minimize the number of evictions here.
We minimize the number of evictions. Yeah, we need to minimize the number of misses actually. So yeah, evictions and bringing in the data, which happens simultaneously, and we'll see why this happens simultaneously also. A miss is basically when we don't have the data and we need to bring it in.
Sir, why is it necessary to move the piece of data from main memory to the cache memory?
Oh, that is just for speed actually.
I'm like, if we kind of add this point that if the memory isn't really referenced later, I won't really add it to my cache memory. So even that would reduce the misses, right?
Sorry, say again.
If that piece of memory is not really referenced later, so I
Yes.
won't add it to my cache memory.
Yes, but that just that just again involves another piece of code, and it just makes the code more complex, and that okay, you are making a different sort of decision and so on. And generally there is this locality. So I mean, this is, so there are two things. First, this algorithm is not actually practical. Okay, so this is, you never know what memory references are going to get generated in an operating system. So this algorithm is used as a benchmark. That
Sir,
okay,
but even in this, like we are seeing like which memory is like the farthest, right?
yes, yes.
Like, how do we know beforehand that which memory would be referenced later?
No, that's what I'm saying. That this is a theoretical analysis where we assume that we know, and then we show that any algorithm actually cannot do better than this, because even if we know, then we can do, we'll have this much misses. Okay, so this acts as a benchmark for analyzing the algorithms which actually don't know.
Yeah, okay, sir. Yeah, thanks.
Yeah. Because yeah, so there are many algorithms which actually, so we'll just quickly look at one of them after we finish this. So like, you must have heard these least recently used or least frequently used and so on. So all these algorithms are compared against this algorithm, which is the optimum algorithm, and see that how they perform. So this gives just a benchmark. This is not a practical algorithm. That's what I said, that this cannot be used in actually operating systems, because this assumes that we know the future, but we actually don't know the future. So that is why this, this is only for theoretical purposes. But this is an optimal algorithm. This is the only algorithm for which you can prove the optimality. None of the other algorithms you can say that they will perform, better than the other, because of course you can come up with these bad cases depending on the future. Okay. Good. So let's just first get something out of the way, which is like, what is a reduced schedule? So it might seem like that, okay, I mean, we can, since we know the future, what we can do is beforehand only we'll bring the data, which which we think will be used later, and, bring in more data, and maybe we can avoid more and more cache misses, right? But this, lemma that we are going to show. So let's first define this. What is a lazy schedule, or reduced schedule? So what is a reduced schedule? It says that don't bring in any data till it's actually requested. Okay. So I mean, a scheduling algorithm has like cache scheduling algorithm has this property that will say that it is a reduced schedule if it does not bring any data before it is actually requested, right? So, and what does the lemma say now, that we are going to show? That for every schedule S, there exists a reduced schedule, let's say S bar, okay, such that, so let's also call the miss M of S. denote the schedule in S, right? So for every schedule S, there exists a reduced schedule S prime such that number of misses in S prime or S bar is less than or equal to number of misses in S. And what is the proof? Can someone guess how will we do this?
Sir, could you explain what a reduced schedule is again?
Reduced schedule is that, okay, so suppose this is the A, B, C, D, E, A, B. So suppose this was the sequence, right? So there is a schedule which when B is requested, right? So suppose it has already A, B, C, D there. Okay. And suppose there was again A is requested. Okay, so suppose this was A, B, C, E, and again A is requested, right? But it does not so A is already there. So what it will do, it will bring in B instead. So suppose B was not there. So it will bring in B at this instance. So A is already there, but it is doing something extra. It is bringing in some extra data at that point, which is not really requested at that point. Okay, so let's say this is T is equal to 1, 2, 3, 4, 5, 6. So at 6, so suppose when E came, we evicted B, right? So suppose when E came, what it became A, E, B, A, E, C, D. Okay. And now when we referenced A, now when the request came for A, what this algorithm did, it put so A is already there, but it still evicted this E, let's say, evict E at T is equal to 6 itself. Evict E and bring in B. Okay. So an algorithm can do that, possibly, right? Because since it can see in the future, then somebody can say, okay, I can be ready. Even though my thing is here already, why do I have to wait for bringing the things later? I'll bring the things now if I can see the future. So what this lemma is saying that this does not give you any advantage. Is that clear?
Yes, sir. Yeah.
Yeah. So why this does not give you any advantage? Okay, so today I'm going a little slow because I think we'll have some time and so that I can make things clear also because this is a slightly involved proof. Okay. So let's look at the proof. So suppose there is schedule S, which now is bringing in, let's say, D, right? Brings in D, which is not referenced yet. Okay. So this is the schedule S. So it has a miss here, right? Now what is the schedule S bar? S bar will be same as, so suppose this is the first time S is doing such a thing. So before that S bar is the same. Now S bar already has this, so D is not requested. Whatever is requested is already there. That is why S could do this thing that he was bringing in D and which is not requested and so on. So S bar serves the request. Okay, so request and waits. Okay, waits till waits till actually D is requested, right? And when D is requested, then it will bring in D, right? And then it uses, then that's where it misses. So maybe now S will not incur a miss because it has already brought in D, right? But now S bar, so S bar will now just pretend that, okay, it has brought in D, but it doesn't do anything. It just serves the request. But suppose, it pretends that it has brought in D, so it pretended that it had one miss, but later it will have one miss when it will actually bring in D, when D will be requested, and that's when it will have one miss. So he will charge this miss. So this is called a charging argument, that we charge the later miss to a previous time when S bar had actually occurred, or since we want to show that S will have any more misses than S, then S had a miss here, and instead of that miss at that point, which S bar had a miss later. Okay, so similarly, like in this algorithm does this. It brings in B, evicts B, and later when B is requested, this algorithm will not have a miss now. So the what will be the equivalent algorithm? The reduced algorithm. It will not bring in B. It will just say, okay, fine. I have to serve the request of A. A is already there. I will not do anything. Now when B comes, they'll be like, okay, fine. Now B is coming, and now we need to evict something, and they will serve that. Okay.
Excuse me, sir.
Yeah.
So suppose that there was one more request between A and B that is already in the stack, suppose C, okay?
Yeah.
And at that point, we just remove D and insert B because our algorithm like predicts the future and takes in the most optimal, like the next.
Say again.
So in that case, we won't get a miss, right?
Say again. I missed
Yeah. So like after like A6, there is C in this in the sequence of instructions.
Okay. Suppose there was a C here. Yes.
Yeah. And so when we reach C, C is already in the stack, but
Yes.
the algorithm can predict the future. So now it just removes D or E and replace it with B.
That's what we were doing earlier in this algorithm, right?
So like it can do it multiple times, so that way it won't have a miss.
No,
Like later.
so this is still a miss, so here whatever is happening, so a miss is basically whenever you evict something and bring something in.
Okay. I thought like the definition of miss was that it is not present.
No. So a miss is actually, so again, think of it like, maybe I, said it in different terms earlier, but think of it actually as, a miss is what costs you. And that's what you want to minimize.
Okay. That explains.
Yeah. So in terms of think a bit more practically in terms of operating system, that fine. I mean, whenever we have to bring in things from the main memory or transfer things to the main memory and so on, that's when that is what costs you. So that's what you want.
Yeah. Okay. Thank you.
Okay. Any other questions about this? So this is just saying that, okay, whatever you are doing right now, you can do later. That anyway you are doing some job for, do that when the request is actually made, and you will not be losing anything. You'll be you'll be as good as the earlier thing where you were doing things before. Okay, so this will come in handy in our. So now we are sort of ready to prove the optimality. Right? So let's say that let D be any arbitrary sequence. Of requests, and let S star denote the schedule with minimum misses.
Excuse me, sir.
Yeah.
The proof for the above lemma done.
Oh yes, it was done. So sorry, I just looked here. So what I did was that okay, so S this S bar does exactly the same at every other point except this point where S brings in something when something else was requested. Okay. So now S bar just follows S, and then whenever this happens, that S brings in D, S bar does not do anything. It just serves the request. Okay, and later when there will be an actual this thing for D, then S bar will bring in D.
Yes, sir.
Okay, so then it will charge it to that, and that's why S bar will not have any more misses than S would have. Okay.
So can you explain the less than equal to sign? Like, why should it not be exactly equal?
Why should it not be? I mean, for every schedule S, there exists a reduced schedule S bar such that this is. I mean, maybe this guy is doing something a lot extra. I mean, which it is bringing in things which will not even be requested in the future.
Okay. Sir, but is it not bringing only those things which are requested in the future? Like,
That we don't know. We are just saying every schedule S. We just know that this is not a reduced schedule. We are
okay.
doing a more general statement here. That's all we are doing.
Yeah, okay, sir.
Yeah.
As in, you are considering a case where, let's say, it first requests B, then evicts it, and then calls it back, even though B wasn't requested for a long time.
Say again, Anushi.
First, it gets B, then evicts it and gets B back, even though
Yes.
B wasn't called for a long
Yeah,
time.
exactly.
Yeah.
And in those cases, like, yeah, I mean, many other things, it can just randomly bring things and so on. So, all I was saying that we are showing a more general thing that if there exists any schedule which is not reduced, there exists a reduced schedule. Sorry, just a moment. There exists a reduced schedule which does an equally good job. So, Arushi, you were explaining Shravan's question, right? Or you
I
had?
was confirming it.
Yeah, okay, yes, you were right. Okay, so this reduced schedule is actually a very subtle point, and we'll see where or why we need that there exists a reduced schedule in the proof of optimality. Okay, so let's start with the proof. So let D be any arbitrary sequence of requests, and S star denote the schedule with minimum number of misses. Okay, and let SFF be the farthest in the future. Farthest. Then what we want to show that the misses that will happen in this is less than equal to S star. So this is our main number, right? That we want to show. If we show this, then we'll be done with the correctness of the algorithm, right? I'm sorry, throat is a bit. Yeah. Good. So is this at least lemma statement clear? This is just the normal optimality lemma statement that whatever the optimum is, algorithm. Okay. I mean, so it should actually be equality, but if we show the less than equal to, of course, it would imply equality. So before we prove that, let's the heart of the proof is something else, and that is going to be an exchange argument. So this proof we'll come to later. So before that proof, let's prove another lemma. Okay. So let S be a reduced schedule. Okay, that makes same efficiency as the farthest in the future for first J steps. Okay, then there exists another reduced algorithm, reduced schedule. Let's say S prime that agrees with SFF for first J plus 1 steps and does not do worse than S. Okay. So let's just show that if we have shown this lemma, then we can show the main theorem. So how will we? So lemma clear though. What is that? Okay, if we have a schedule which agrees with the partition in the future, then we can find another schedule which agrees with partition in the future, J plus 1 steps. So can someone tell me how will we get this? Should I show the statement again? Anyone? Okay, so let's start with, so what do we want to show? We want to show that there exists an optimal or this SFF is optimal, right? Good. So now what we want to do that we want to do this exchange argument sort of, right? So let optimal. So let S star be that. Okay. Or if you don't want S star, let's say S double star, which is so M of double star, M of S star, right? Why? Because of previous lemma. That this is. Can you hear me?
Yes, sir.
Yeah. Okay. Yeah. Thought there was some problem because also. Okay. Yeah. So I think there is some lag because of my lag. Okay. There is a little bit, I think, but okay. Let's hope it goes on a bit. it doesn't cause too much of a... Audio is breaking. Yeah, I thought there is some problem with the internet. Can you hear? Can you hear me now?
Yes, sir.
Okay. Yeah, so it's not going completely, at least it's yeah. But it is slow. It is slow. Okay, just let me try once more. Just a moment. Okay, let's see now whether it works. Can you hear me now? Can
Yes,
someone...
sir.
Yes.
Yes, sir.
Okay, but I'm not very sure. So I apologize beforehand. It might I might try to go to hotspot or something if this does not work very well. Okay. So just be but yeah, please type in the chat if you can hear me now. Or if it's not clear, I'll go to hotspot. Okay, so audio is breaking still. All right. Yeah. Okay. Any better? Can you hear me now?
Yes, sir, you are audible.
Okay, good. Thank you. So hopefully this works. I'm using hotspot right now. So let's see. Yeah. Okay. Anyway, so we were talking about these schedules. So what I was saying that okay, let's S star was this optimum schedule, and what I did, I took a reduced schedule S double star, which is as good as S star that exists from the previous lemma. And now what I'll do, I'll take this S star and start applying this other lemma. So S star maybe initially agrees on with SFF on 0 steps. Then I can get S star 1 that agrees with SFF on 1 step. Okay, which is also a reduced schedule. Then I can get S star 2, which on 2 steps. And all of these make at most as many mistakes as the other one, right? And finally, in the chain, I'll get something which agrees with SFF on every step. So what I'll get, MSFF, and that will complete my chain, and that will do the proof. Is that clear? So this 1, 2 and all basically represents how many steps this algorithm agrees with SFF, which is the farthest in the future algorithm. Okay, so that means that this lemma is the central thing. Like, this lemma is the hard part of. If we show this lemma, then this proof is there. Is the proof clear of the previous lemma, given the statement of the next lemma?
So should we not prove that SFF is a reduced schedule?
That is inductively we are maintaining, right? So SSF will turn out to be reduced schedule, and SFF is anywhere reduced schedule because by definition that if we go to SFF, what is SFF? Suppose DI needs to be brought into then only something is evicted. It is never like, whenever something is needs to be brought in, it will only be brought in then. It will not be brought in before. So the SFF is actually reduced by definition. And also, when we are going by this chain, what does the lemma say? That let S be a reduced schedule, and then S prime will be another reduced schedule, which agrees with SFF on one more step, right? So finally, we'll get to SFF. Arshi?
Yes, sir.
Okay. Any other question about this? Okay, so now we'll get to the heart of the proof. So yeah, so this was like kind of the easy part, I would say. But still some subtle things that we need to be careful about when proving this. Okay. Okay. So we have this S is given, agrees with SFF on J steps. Okay. Now we need to design this S prime, which agrees with on J plus 1. Need to design that. So, of course, first we should make S prime to agree with S or JS, this SFF on J steps. I mean, this it needs to do at least, right? So let the J plus 1th request be for item D. Okay, good. So D is equal to dj plus 1. All right. So also since S and S prime have the same uh, initial J steps, the contents of the cache at or after the J requests are the same. Okay, good. So whatever S has, same thing S prime has. Right? Now, if right, now if D is there in the cache already, then what happens? Then S does not do anything. S prime also, might not do anything because both are reduced. So we can put S is equal to S prime, and we are good. Why? Because SFF also will not do anything because SFF is also a reduced schedule. So S is equal to S prime, and then we have whatever M of S prime is less than equal to M of, because of course S is equal to S prime. If D is there in the cache, right? So this is not the hard part. Similarly, if D is not there, but S and SFF remove the same element or evict the same element. Then also we are good. Then also S prime can just copy S, right? So S prime is equal to S, and then again we are good. But now the problem is if they evict different item, okay? So what if they evict? So what is they? They is S and SFF. Different items. Okay, good. So suppose this was the initial thing. So they had two items, E and F. Okay, and D needs to be brought in. D needs to be brought in. And so let's say that S prime evicts E, SFF evicts E. And S evicts F. So now there is a problem. So now we cannot be same as S because SFF is doing something else and S is doing something else, right? And what is our goal? Our goal is to agree with SFF but not do more than what S is doing, but still be close to S, right? So we want to match SFF at one more step. So we want to be evicting E right now, but later we want to be as close to S as possible, right? So now what happens? What becomes the cache, for example? So everything else remains the same. So S prime now, of course, is going to follow the SFF cache at this point. So what is going to be their cache? Their cache is going to have D here and F here, right? And what is going to be S ka cache? S ka cache is going to be D here and E here, right? So now they are in different states. So now we need to be careful while designing S prime that what will S prime do.
Excuse me, sir.
Yeah.
Sir, in SFF,
Yeah.
we choose the one which is farthest in the future, right? So
Yes. That's
the one which is never in the future, it is considered farther than all others, right?
yes. And then you can break the size arbitrarily. Yes.
So like, can I say that S will be missing F in future definitely, and SFF will be missing E, and SFF will be missing E in future definitely.
Missing meaning?
Like later when I get a request for E, SFF will be missing E. We'll
Yes.
have a miss when E is referenced, whereas in S, we'll have a miss when F is referenced. But
Yes,
in
that's
S,
correct.
we can again have a miss when E is referenced. So with S, we can have two more misses, but with SFF, we'll have only one more miss.
Maybe I'm I just. So you're saying that with SFF we can have only one more, but we have to compare S prime with S, right?
Yeah, with S prime follows SFF for one more step, right?
Yes, it just follows SFF for one more step.
So with S prime, we are evicting E.
Yes.
And E is farthest in the future.
Yes.
So with S prime, when E is referenced later in future, with S prime, we will be missing E definitely because it won't be in the cache.
Yes, that's correct.
And with S, we will be missing F because F won't be in the cache for with S.
Yes.
But with S, we can end up missing E as well because we aren't really sure when E is referenced, will E will be in the cache for S or not.
Yeah, but I mean, so we need to be slightly more precise than that, right? Because this E is there, and you're saying that we might end up missing E, we might not, and yeah. So these things are, so that's what we need to pin down a little bit. So, I mean, yeah, if you have a formal proof, we can discuss that, later. So let me try to do what I want to do, and then we can, take this later because we are already over time. So just a little bit, go slowly and then get it done with, and then we can take the question. Okay, Sean?
Yeah, sure, sir. Yeah.
Okay, good. Okay, good. So now how do we get S prime, right? So finally, we want to compare the miss of S prime with misses of S, right? So what we want to do, we want to get as close to S as possible, as soon as. So what happens if, like we saw earlier, if their cache content becomes same at any point, then after that S prime can just follow S and we are good, right? So if cache is same, follow S after that. So the idea is going to be to make the cache same, okay? So what is the difference right now? Difference is S has E, S prime doesn't, and S prime has F, S doesn't. Okay? Cool. So now the simplest thing that is like if you see at these things that, okay, now if S evicts E at some point, right? Then the SFF or this S prime is good. If S evicts E at some point, then we are good. So let's see that if any of these two events occurs, so what is the first event? If S evicts E. Okay? So if S evicts E, then to bring in something, okay, that is not F basically. So suppose S evicts E and bring in something that is not F. Okay? Then what will S prime do? S prime will evict F. So let's just do this like. So S prime has D and F, and S has E and F, right? Sorry, S prime, S has E and D. And now suppose S evicts E to get something that is not F. Okay? Then what does this do? What does S prime do? S prime will evict F and bring the same thing. So bring something, let's say that is like some D prime. So both will get D prime, and after that, this will also have D prime F, D and D prime, and this will also have D and D prime. Okay? So if E gets evicted by S also, then we are good because we evicted E and then S also evicted E. So we became like same as S. Okay? So in this case, we are good. What is the second case? Second case is that if there is a request to S, request to F, right? And S evicts some E prime. Okay? So again, let's say we have D and F in S prime, and S has D and E, right? And now S gets a request for F and it evicts some E prime. So S now needs to get F somewhere. Now if this E prime is equal to E, suppose E itself is getting evicted in S, then we are good because then we have already F and then we don't need to do anything. And then if S is putting F here itself, then we get the same content, same cache, and we are happy, right? Now suppose E prime is not equal to E, okay? So if this E prime is not equal to E, so suppose this E prime is somewhere here and we are putting the D here, putting F here. So, wait, I am doing something wrong and nobody is pointing it out. No, I mean, I didn't do wrong, but here I should now put E back. Okay, so S had D and E. No, it did not have D and E. Yeah, S had D and E, and now it got a request for F, and E prime is evicted. So if that E prime is E, then we get D and F, and then we get the same cache in both the cases. Now, if F is going for some other E prime, right? That means this E prime is there in uh, in both of them, S and S prime, because this is the only place that they differ, D and E and D and F. So now for this E prime, what will S prime do? S prime will evict this E prime and put what there? What should S prime do there? Put there to make the cache same. So after this will become F. It should become put E back there, right? So S prime would put E back there, so it will become EDF. And what will S do? S have already put F in place of E prime, E. Okay? So this is S prime after that, and this is S after that. So if E prime not equal to E, what is S prime doing? Evict E prime and put in E back.
So how do we put in E back? Like if it
At the
hasn't been
place,
referenced,
at the
like
place
if
of E.
it hasn't been referenced, right?
Good point, Shravan. So what Shravan is saying is that it has not been referenced, so we are breaking our rule that it is not a reduced schedule that we are getting to. So the S prime that we are getting is not reduced. But then we can get another schedule S double prime that is reduced using the previous lemma such that M of S double prime is not more than M of S prime, right? And now this M of S double prime actually agrees because first J plus 1 steps S prime behaves as reduced. So those J plus 1 steps even S prime agrees with SFF on J plus 1 steps and S double prime is reduced. So this is why we needed to show earlier that there exists a reduced schedule that does these things. And where are we using the reduced schedule in this proof? We are using initially that when we got the first one, when we were saying that, okay, if D is there, if D is already there, then we need to make sure that, okay, S is not doing something crazy. And we can easily match S and S prime there. So that is why we need reduced. And now since we need reduced, as Shawn pointed out, this S prime that we were getting was not reduced, but we can make it reduced because we have shown it earlier in the proof. So now S double prime is a reduced schedule that agrees with SFF on J plus 1 steps, and M of S double prime is less than or equal to M S prime. And you saw that here there was no place here whenever S was making an eviction, then only S prime was making an eviction. Here also, if E prime is equal to E, then in fact S prime did not need to make any evictions. If E prime is not equal to E, then S prime made one eviction, right? So in every case, what we were getting, M of S prime is less than equal to M of S. Yeah.
Yeah,
There was-
excuse me, sir. Why do you want to get as close to S as possible?
Because we want to compare it finally with S7.
Hmm.
What is the lemma statement?
Yeah, that the
Lemma-
Hmm.
Because if we deviate from S, then S is doing something else and S prime is doing something else. How will we compare?
Hmm.
So like what we're trying to prove is between like during the stage when S prime and S are distinct, in that phase S prime makes less number of misses than S. Because
First, what is the phase
Uh,
identity?
a phase as in like till step J, S and S prime are same, then they'll become different for some time, after which we'll get back to S.
Yes.
So during this time, S prime will make lesser number of misses than S.
Yeah, exactly. And also one thing, so Shravan, you are right. And why these things are bound to happen, by the way? So what if these things don't happen or something? So first point is, if these things don't happen, then the S prime can continue as S anyway. Because what is the only difference? The only difference is E and F. So if E gets evicted from S, that is one difference can be there, or if F gets difference, that can be one difference that is there. Okay? There is another possible difference that you might think of. What if S prime, there is a request, for E? Then what would happen? What if there is a request on E?
At what stage
No,
will
so
the request for E will be
exactly.
will-
So can this happen? So at what stage? So after this J thing. So we looked at these two cases, right? If S evicts E, this is one case that we looked at. Okay. Another case was that, okay, what if there is a request for F here in S? But if there is a request for F, then S does something and then we got back to the same cache. But what if there is a request for E? Then S can serve it very well and S prime will be problematic because S prime does not have E.
F comes before E, right? That cannot happen.
Exactly. So the thing is that whenever if E is requested, then definitely F is going to be requested first. So we would have gotten to the same cache point where both caches will be the same after that. So F will always be requested first before E, and that is why this particular problem that I'm mentioning, that what if E gets requested, will not matter. So these three are the only cases when some problems can happen. Everything else they follow each other. One is if S evicts E, then we know what to do. If if there is a request for F, then we know what to do. Now, if there was a request for E, that cannot happen. I mean, that can only happen after the request for F has been made, and then we have the same cache already. So that is where we are using the farthest in the future property. That the request for E will only come later than the request for F. Okay.
So can you again explain that S double prime part?
Okay, so S double prime part. So right now, what did we do with S prime? So S prime, we were looking at the second case when there is a request to F. Okay. If you keep responding, I'll be like, it will be easier for me, Anshuman. Okay.
Yes, sir.
Yeah. So if there is a request to F, okay. Now there were two cases. So F needs to be brought into S. right?
Yes.
So the first case was when E was evicted. If S evicted E prime equal to E, then we are good because then S prime has already sort of done that. So S prime doesn't need to do anything. It does not incur any risk. Okay,
Right.
so that's taken care of. Now, if E prime is not equal to E, that means S is evicting some E prime and putting some F in there. Okay, and what did I say that S prime will do now? S prime will also evict E prime and put in E instead. So now S prime is doing something that it does not need to do, that a reduced schedule does not do, that a lazy schedule does not do. So S prime now is not a reduced schedule.
Okay.
Okay, so now we get the schedule which does not incur more misses than S, but it is not a reduced schedule. But the lemma statement says that there exists a reduced schedule S prime because we need this to be reduced for the induction to be applied again and again in the previous rules. How can we get back every single time? Because every single time whatever we are getting is a reduced schedule form. Okay, so we need a reduced schedule. So
Yes.
now for reduced schedule we go from S prime to S double prime. Okay.
And we know that the difference between S prime and S double prime will only occur after that point.
Exactly. After the J plus 1.
Okay.
So aren't we really using the same lemma which we're trying to prove?
No, where?
Like there would exist S double prime which would be reduced.
No, this S double prime is previous lemma. This is the previous lemma which said that for every schedule there is a reduced schedule S prime such that the misses are less. And we are using the proof of this lemma, sort of, that how do we arrive at that, this S bar? We arrived at, we only make the changes after they, differ, right? Or when actually was made, some non-reduced choice. Okay, so we are not using the same lemma. So yeah, it's a bit like, might sound a bit like, convoluted and so on, but that is what, this is a more involved proof. And like you would need to like have another look at it to understand it completely. Even I I hope I was able to at least give the, main details. But I think it would require going over it once more for you guys to, get it completely internalized. But I find it to be a very nice, and proof. So, and all the details are, the certain things are, necessary sort of for it to work. And I hope you get it.
So can you go to lemma 2 once?
Yeah,
The
sure.
final step.
This one.
So here S star is an is supposed to be optimal, right?
Yeah.
Okay. Yeah.
So S star is optimal. From S star we got to S double star, which is like, does not have any whatever these is reduced, does not have, and then from that we kept reducing, or I mean kept getting towards SFF.
So S star has to agree with SFF in some prefix of at least length 0.
That we do with S double star because S star might not be reduced.
Okay. Yeah. Okay. All right.
Okay.
Yes, sir.
Good. So, any other questions? Quick questions? Okay, we have taken a lot of time, and I apologize for that, but I hope, this was worth it. Any questions? Cool. So, if not, then thank you for coming, and see you guys on Tuesday. And yeah, by Tuesday, I'll try to also prepare the assignment and send it out. Thank you.